Machine learning, ML, is a powerful branch of artificial intelligence, AI, focused on developing algorithms that enable computers to learn from data, identify patterns, and make decisions with minimal human intervention. With roots in statistics, data mining, and cognitive science, ML has evolved significantly over the past few decades, driven by advancements in computational power and data availability. Today, it encompasses a variety of approaches and models that find application in industries like healthcare, finance, automotive, and beyond. Here's a deep dive into the concepts, types, and recent advancements in machine learning, with examples to clarify its practical impact. 1. Fundamentals of machine learning. Machine learning aims to create models that generalize patterns from historical data to make predictions or decisions on new, unseen data. At its core, ML involves three main steps: data collection and pre-processing. Gather and prepare relevant data by handling missing values, normalizing, and encoding categorical variables. Model building. Using algorithms to train a model involves adjusting the model parameters to minimize error. Evaluation and testing. Assessing the model's accuracy on a separate dataset, testing set, and refining it as needed. ML models generally operate on the principle of reducing prediction error and improving their accuracy over time with more data and experience. 2. Types of machine learning. There are several types of machine learning, classified based on how models learn from data. Supervised learning. In this method, models are trained on a labeled dataset, which means each data point has an associated output label. The goal is to learn how to map inputs to outputs. For example, in email spam detection, labeled emails, spam or not spam, are used to train a model to predict new email labels. Common algorithms include linear regression, predicts a continuous outcome based on one or more input features. It's used in applications like predicting housing prices. Decision trees and random forests are used in classification tasks, such as predicting whether a loan applicant will default based on historical loan data. Unsupervised learning. In unsupervised learning, models work with data that has no labels, attempting to identify hidden patterns or groupings. For example, market segmentation often uses clustering algorithms to group customers based on purchasing behavior. Key techniques include K-means clustering. This technique groups data points into clusters based on their features, which is helpful for customer segmentation and marketing. Principal component analysis, PCA, reduces the dimensionality of data. It is often used in data compression and noise reduction. Semi-supervised learning. This approach combines labeled and unlabeled data, making it useful when obtaining labeled data is expensive or time-consuming. For instance, in medical imaging, a small number of annotated images, like MRI scans, are combined with a more expensive set of unlabeled images to improve disease detection. Reinforcement learning, RL. RL is inspired by behavioral psychology and is used to train agents to make sequential decisions. An agent learns by interacting with its environment, receiving rewards or penalties based on its actions. This is foundational in applications like game playing, for example, AlphaGo and robotics. 3. Key machine learning algorithms. Machine learning algorithms vary widely depending on the problem they solve. Support vector machines, SVM. SVM is a classification technique that separates data points into different classes by finding a hyperplane that best divides the classes. It's effective in image classification tasks. Neural networks. Inspired by the human brain, neural networks consist of layers of interconnected nodes, neurons, that process data. Deep neural networks with multiple layers, deep learning, are instrumental in image and speech recognition. Gradient boosting machines, GBM. This ensemble method combines weak learners, typically decision trees, to create a robust predictive model. XGBoost, an implementation of GBM, has performed well in structured data competitions like Kaggle. 4. Machine learning applications and examples. Machine learning's adaptability makes it ideal for various real-world applications. Here are a few examples. Healthcare. ML models analyze medical data to assist in diagnosis, treatment planning, and drug discovery. For instance, convolutional neural networks, CNNs, detect abnormalities in medical imaging, for example, identifying tumors in X-rays. Finance. ML algorithms are employed in fraud detection, where anomaly detection techniques flag unusual transactions, reducing fraudulent activity. Predictive models also help in algorithmic trading and credit scoring. Retail and e-commerce. Recommendation systems use collaborative filtering and other ML techniques to provide personalized suggestions to users. For example, Amazon's recommendation engine uses supervised and unsupervised learning to analyze purchase patterns and recommend products. Natural language processing, NLP. NLP enables machines to understand and generate human language. Applications include chatbots, sentiment analysis, and language translation. OpenAI's GPT-3 and GPT-4, large language models, use massive datasets to generate human-like text, significantly advancing the field of automated content creation and translation. 5. Advanced concepts and trends in machine learning. Deep learning, DL. Deep learning is a subset of ML that relies on neural networks with many layers. With computational power and data advancements, DL models have achieved remarkable success in image and speech recognition, natural language processing, and more. For example, transformer architectures, for example, BERT, GPT, have set new standards in NLP. Transfer learning. This involves leveraging a pre-trained model on a large dataset to apply to a related task with less data. Transfer learning has shown exceptional success in fields like medical image analysis, where labeled data is scarce, but pre-trained models can be adapted to new domains. AutoML, automated machine learning. AutoML automates selecting and tuning machine learning models, making them accessible to non-experts. Tools like Google AutoML and H2O.ai reduce the need for specialized knowledge in model selection and optimization. Explainable AI (XAI). Machine learning models are deployed in sensitive areas like healthcare and finance, and interpretability has become crucial. Explainable AI aims to make models more transparent, enabling humans to understand the decisions made by complex models like deep neural networks. 6. Challenges in machine learning. Despite its capabilities, machine learning also faces significant challenges. Data privacy. The use of personal data in ML raises privacy concerns. Models need large data sets, but ensuring the security and privacy of user data remains a top priority. Bias and fairness. Machine learning models can inherit biases in training data, leading to unfair or discriminatory predictions. Ensuring fairness in ML is a complex, ongoing challenge, especially in sensitive fields like criminal justice and recruitment. Overfitting and generalization. A common issue in ML is that overfitting occurs when a model performs well on training data, but poorly on new, unseen data. Regularization techniques, cross-validation, and careful feature selection help mitigate this issue. Computational costs. Training large ML models, especially in deep learning, is resource-intensive. Developing energy-efficient models and optimizing computational processes are crucial as models continue to grow in size. 7. The future of machine learning. As we look toward the future, machine learning continues to evolve rapidly, with trends pointing toward more efficient, interpretable, and ethical models. Federated learning. To address privacy issues, federated learning trains models across decentralized devices without transferring data to a central server. This method is already used in personalized applications like predictive text on mobile devices. Ethical AI and governance. As ML becomes ubiquitous, ethical considerations, regulatory frameworks, and governance models are essential to ensure responsible use. Organizations worldwide are establishing guidelines to address issues like data privacy, bias, and transparency. Quantum machine learning. The field explores quantum computing to accelerate ML processes. Quantum computers hold the potential to handle computations exponentially faster than classical computers, which could lead to breakthroughs in model training times and data processing. In conclusion, machine learning has reshaped how industries and individuals approach data, transforming processes across sectors from healthcare to retail. ML will likely become even more embedded in our daily lives as it matures, enabling technologies that learn, adapt, and make decisions autonomously. With advancements in computational efficiency, ethical frameworks, and interdisciplinary research, the future of machine learning is both promising and profound.